Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The early 20th century presented physicists with a conundrum: blackbody radiation, classical physics, triumphant in so many arenas, stumbled when attempting to explain the spectral distribution of energy emitted by a perfect blackbody, an object that absorbs all incident electromagnetic radiation. Wien's displacement law, derived from thermodynamics, accurately described the spectrum at high frequencies, yet failed miserably at lower frequencies, predicting an intensity approaching zero, contrary to observation. Conversely, the Rayleigh-Jeans law, rooted in classical electrodynamics and statistical mechanics, successfully predicted the spectrum at low frequencies, but spectacularly failed at high frequencies, leading to the infamous ultraviolet catastrophe, where the energy density diverged to infinity. Enter Max Planck, who, in 1900, proposed a revolutionary hypothesis: energy is emitted and absorbed in discrete packets, or quanta. The energy of each quantum is proportional to its frequency, expressed as E equals h nu, where E represents energy, h represents Planck's constant, and nu represents frequency. This quantization hypothesis, though seemingly arbitrary, miraculously produced a formula that perfectly matched the experimentally observed blackbody spectrum. Planck's law, as it became known, marked the birth of quantum mechanics, yet its underlying justification remained somewhat ad hoc. It was a brilliant fix, a mathematical sleight of hand that lacked a deeper, more principled foundation. In 1994, Satyendra Nath Bose, an Indian physicist then at the University of Dhaka, provided precisely that foundation. Bose approached the problem of blackbody radiation from a novel perspective, one that sidestepped the problematic assumptions of classical electrodynamics. His key innovation lay in treating photons, the quanta of light, as indistinguishable particles that could not be individually identified or labeled. This seemingly subtle shift had profound consequences. Classical statistical mechanics, embodied in the Maxwell-Boltzmann distribution, assumes that particles are distinguishable. Imagine, for instance, tracking individual gas molecules within a container. Each molecule, in principle, possesses a unique identity and trajectory. Bose realized that this assumption simply did not apply to photons. Photons of the same frequency are fundamentally identical. There is no way to distinguish one from one. Bose's revolutionary insight lay in developing a new statistical method to count the number of ways to distribute photons among different energy states. He divided the phase space, a six-dimensional space representing position and momentum, into cells of volume h cubed. He then calculated the number of ways, denoted by W, to distribute a given number of photons with a specific energy among these cells, considering that photons within a cell are indistinguishable. The formula he derived for the number of states, given by W, equals the product over all energy levels I of the quantity, G sub I plus n sub I minus 1 factorial, divided by n sub I factorial times G sub I minus 1 factorial, became the cornerstone of his theory. Here, G sub I represents the degeneracy of the ith energy level, and n sub I represents the number of photons occupying it. This approach, rooted in combinatorics, yielded a significantly different counting method than the classical Maxwell-Boltzmann statistics. By maximizing the entropy, a measure of disorder, subject to the constraints of constant total energy and constant total number of photons, Bose derived Planck's law without any reference to classical electrodynamics. He had effectively derived Planck's radiation formula solely from the principles of statistical mechanics and the hypothesis of light quanta, treating photons as intrinsically indistinguishable particles. Bose, after struggling to get his work published, sent his manuscript to Albert Einstein. Einstein immediately recognized the significance of Bose's work. He translated the paper into German and submitted it to Zeitschrift für Physik, adding his own endorsement. In a note, Einstein stated that Bose's derivation represented an important step forward and that he would elaborate on its implications in a forthcoming publication. True to his word, Einstein extended Bose's statistics to matter particles, specifically to ideal gases. This generalization led to a startling prediction that at sufficiently low temperatures and high densities, a significant fraction of the particles in an ideal gas would condense into the lowest energy state, forming what is now known as a Bose-Einstein condensate. This condensation represents a macroscopic quantum phenomenon, where a large number of particles behave as a single quantum entity. Bose's 1924 paper constituted more than a derivation of Planck's law. It inaugurated an entirely new field of quantum statistics. His work provided a rigorous foundation for the quantum theory of radiation and opened the door to the study of novel quantum phenomena, setting the stage for the development of Bose-Einstein statistics and the prediction of Bose-Einstein condensation. The implications of his work continue to resonate across diverse areas of physics, from condensed matter physics to quantum optics, solidifying its place as a pivotal contribution to 20th century science. Bose's ingenious approach did more than reinterpret Planck's law. It laid the groundwork for a revolutionary understanding of particle statistics, prompting Albert Einstein to extend Bose's methodology to encompass material particles. This bold generalization posited that under conditions of sufficiently low temperature and high density, a substantial fraction of particles within an ideal gas would collapse into the lowest energy state, coalescing into a Bose-Einstein condensate, a phenomenon characterized by macroscopic quantum behavior. Einstein's extension, far from a trivial application, fundamentally reshaped our comprehension of matter at the quantum level, forecasting a state where countless particles act in concert as a single quantum entity. The theoretical conditions for Bose-Einstein condensation demand exceeding low temperatures and elevated densities, specifically the de Broglie wavelength, inversely proportional to the square root of temperature and proportional to the square root of mass, must become comparable to the interparticle spacing. At this juncture, the wave functions of individual particles begin to overlap significantly, losing their individual identities and merging into a collective state. This quantum degeneracy gives rise to the condensate, a coherent assembly residing in the lowest energy level. While the prediction of Bose-Einstein condensation remained theoretical for several decades, the experimental verification arrived in 1995. Eric Cornell and Carl Wieman, working at the University of Colorado Boulder, achieved this breakthrough using rubidium atoms. Through precise laser cooling and magnetic trapping techniques, they lowered the temperature of a dilute gas of rubidium atoms to approximately 170 nanokelvins, a temperature nearing absolute zero. At this point, the atoms underwent a phase transition, and a significant number of them condensed into the lowest energy state, forming a visible Bose-Einstein condensate. This experiment marked a watershed moment in physics, confirming a long-standing theoretical prediction and opening up new avenues of research in quantum phenomena. Following Cornell and Wieman's pioneering work, Bose-Einstein condensation observed in a variety of other systems. These systems included different atomic species, such as sodium, lithium, and hydrogen, as well as more exotic systems such as exciton pulmaritons in semiconductor microcavities. Each system presents unique challenges and opportunities for exploring the properties and applications of Bose-Einstein condensates. Bose-Einstein condensates play a pivotal role in understanding superfluidity and superconductivity. Superfluidity, the frictionless flow of a fluid, arises from the Bose-Einstein condensation of helium-4 atoms at low temperatures. In this state, the helium-4 atoms form a condensate, allowing them to flow without viscosity. Superconductivity, the disappearance of electrical resistance in certain materials at low temperatures, explained by the formation of Cooper pairs of electrons that behave as bosons and undergo Bose-Einstein condensation. The formation of this condensate enables the electrons to flow through the material without scattering, resulting in zero electrical resistance. Bose's work furnished a nexus between quantum mechanics and statistical mechanics. Prior to Bose's derivation, these disciplines operated independently. By treating photons as indistinguishable particles and employing combinatorial arguments to count the number of microstates, Bose bridged the gap between quantum mechanics, which governs the behavior of individual particles, and statistical mechanics, which describes the behavior of large ensembles of particles. His approach provided a consistent framework for understanding the statistical properties of quantum systems. Bose-Einstein statistics have evolved into a fundamental framework for understanding the behavior of bosons, particles with integer spin, bosons, in contrast to fermions, obey different statistical rules due to their indistinguishability. This distinction has profound implications for the behavior of matter and energy at the quantum level. Applications of Bose-Einstein statistics span a wide range of fields. Photonics, the science and technology of light, relies heavily on Bose-Einstein statistics to describe the behavior of photons in lasers and other optical devices. Quantum computing explores the use of quantum phenomena, such as superposition and entanglement, to perform computations. Bose-Einstein condensates have proposed as qubits, the fundamental building blocks of quantum computers, owing to their coherence and controllability. Philosophically, Bose's work challenged notions of particle distinguishability. In classical physics, particles are considered distinct entities, each labeled and tracked individually. However, in quantum mechanics, identical particles become indistinguishable. This indistinguishability has profound implications for the foundations of quantum mechanics and our understanding of reality. Bose's 1924 paper on Planck's law stands as a foundation of quantum statistics. Its influence resonates through diverse areas of physics, shaping our understanding of the quantum world. His work has stimulated research into Bose-Einstein condensation, superfluidity, superconductivity, quantum in reflection. The impact of Bose's derivation of Planck's law cannot be overstated. His seemingly simple, combinatorial approach to counting photons revolutionized our understanding of quantum statistics and opened the door to new fields of physics. His legacy endures as a testament to the power of innovative thinking and the profound impact of fundamental scientific discovery.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.